Hi everybody, this is Mr. Zarzak, and in this screencast I'm going to be working a complex problem involving work. So let's get right to it. Alright, so it says let's try a difficult problem. It puts together a lot of concepts, and that's right. There's going to be a lot of physics we're going to need to do for this. Alright, so it says a 20 kilogram lawnmower starts at a velocity 10 meters per second when Bob hits a rough patch. He's applying a force of 50 newtons down and to the right at an angle of 70 degrees below the horizontal. The coefficient of friction is 0.30. What is the total work done by Bob from the moment the mower starts to slow down until it stops? All right, so Bob is pushing along his lawnmower, and he must hit a rough patch. Maybe he's on some well-trimmed grass, and he hits some really thick grass, or maybe he's on the sidewalk, and he moves onto the grass. Okay, but he hits something that restricts his motion. Okay, so that we're going to treat that like a frictional force. This is what's the total work done by Bob from the moment the mower starts to slow down until it stops. So we want to be able to use work, which is force times displacement. Now, we've got Bob's pushing, okay, and it's at an angle, but we could figure out the direction of that force that acts in the direction that the lawnmower will be moving, which, according to this picture here, would be to the right, but we don't know the displacement, okay? So in order to solve this problem, we must first get the displacement. In order to get the displacement, we're actually going to have to look at this in terms of forces, see, because Bob's lawnmower is moving, but then it eventually comes to rest, which means it has to accelerate, okay? And that's kind of the key there, is we need the acceleration to get to the displacement, and then the displacement to get to the work, all right? So if you didn't follow that line of reasoning, that's okay. Hopefully, as the problem lays out, it'll start to make more sense. So I'm going to start this by applying Newton. And by what I mean by that is I'm going to draw a free body diagram for the lawnmower. Okay, so there's a lot of review that's involved with this. All right, the forces that act on the lawnmower is it's got some mass, so it means it's got some weight. All right, the mass is given, it's 20 kilograms, so it's being pulled down by the force of gravity, which we call the weight. All right, now there's normal force, but I'm going to wait to draw that because we've also got Bob pushing. Bob is pushing down at an angle of 70 degrees. Okay, so I'm just going to draw that arrow to represent Bob pushing here. So I'll call that the force of Bob. All right, and because that arrow is pointing down to the right, there's a downward component to that force. There's also a rightward component, but the point is that the ground has to support both the weight and has to counteract that downward pushing force in order to keep the lawnmower in equilibrium up and down. Okay, so that normal force arrow is going to be bigger than the weight. And then, of course, we've got that frictional force. The lawnmower is moving to the right, so then friction's got to be acting to the left here. Okay, so I'm going to draw a little arrow to show the frictional force. There we go, F of F for force of friction. Okay, now I'm going to take that Bob arrow, okay, and that's the one that's at an angle. All right, so I'm going to go ahead and break that up into components. That's the first thing that I'm going to take care of here. All right, so again, that's the Bob pushing. All right, so now it says here in the problem, let's see, he's applying a force of 50 newtons down right. That's an angle of 70 degrees below the horizontal. Okay, so the horizontal, so here's a horizontal line. All right, and let's just make that, it's really just there to show horizontal. So this angle of 70 degrees is below the horizontal. So if I went below the horizontal, some angle of 70 degrees, okay, that's our little theta. All right. Here's my components. All right, the vector points down and to the right, so the components point down and to the right. All right, so let me go ahead and draw those components in. All right, and like that. There we go. Okay, so then this would be my x component of Bob pushing, and this is my y component of Bob pushing. All right, so looking at where I've got my angle, all right, Bob is the hypotenuse. All right, so that means that the x component is going to be Bob times cosine of theta. Okay, Bob pushes with a force of 50 newtons. Okay, so we could solve for that. I don't need it right now, so I'm just going to wait and just kind of set this up conceptually, and then I'll solve it all together here at the end. All right, Bob y is going to be Bob pushing times the sine of the angle. Okay, so just remember, we've got opposite and hypotenuse is for the sine function, adjacent and hypotenuse is for the cosine function. Okay, now I find it useful simply because it's so easy to do this. In Notability, I'm just going to take and I'm going to draw a new free body diagram that doesn't have the diagonal, but just has the components, just because I think it's going to be easier for me to see what it is that I need to do. I made that one a little goofy. Okay, so put that in there, put that in there. Okay, so then we've got this. This is the bob pushing downwards. So bob Y and bob pushing sideways components. Okay, so now I can go ahead and write some equations. All right, I'm interested in the acceleration. All right, so just to kind of recap, Bob is pushing the lawnmower, he hits this rough patch, and he slows down. Okay, so the lawnmower is not going to move up or down. The acceleration is in the X direction. So if I look, I say, look, I have Bob pushing in the X direction in one direction, and then I have friction opposing that. Okay, and it's the difference between these two forces that's going to cause the lawnmower to accelerate. All right, now Bob pushing in that X direction, that's our FB cos theta. Okay, Bob pushing is given, and so is the angle, so I've got that. All right, that friction force, though, I don't know what the friction force is, but I do know the coefficient. All right, and so kind of one of the keys to this problem is remembering that friction is the force that makes physics fun. Or in other words, F of F is equal to mu F of N. The mass of the lawnmower is given. Okay, so if I knew the normal force, I could get the acceleration. All right, I don't currently know the normal force, but I have the ability to get it. Okay, I look up and down, and I see, look, the normal force is acting upwards. I have a downward push from Bob, and I have the weight of the lawnmower as well. And that together tells me about the acceleration in the Y direction. See, like up here, this is the acceleration in the X direction. Okay, in the Y direction, the lawnmower is in equilibrium. In other words, him pushing doesn't cause the lawnmower to go down into the ground because the ground's there preventing it from happening. Okay, so if I just do a little bit of rearranging here, all right, normal force minus Bob Y minus FG is equal to 0, so that means that normal force has got to be equal to Bob Y plus the weight together. Okay, and I can expand this out just a little bit. So let's see, Bob Y, that's the FB sine theta. Okay, and weight, or the force of gravity, is mg. Okay, so now I have an expression for the normal force here and back up here. So what I'm going to do is I'm going to sub that in, okay, to that top equation. All right, and I'm going to use that to solve for the acceleration. Okay, so let's go ahead and do that. So substitution for the normal force. All right, so what do I have here? I have force of Bob X minus, oh, excuse me, I already wrote that out, FB cosine, which is Bob X, pardon me. Okay, minus mu times my normal force, where my normal force is just all of this in here. Okay, so that's mu F of N. All right, and then that together equals ma. Okay, so now to get the acceleration, all I have to do is just divide out the mass. And there we go. All right, so my acceleration is going to be equal to this mess, which I would have to calculate, but hey, I can do that. Okay, I can plug numbers into my calculator, and we will. All right. Once I solve for that acceleration, okay, from there, once I know the acceleration, then I can get the displacement. Now, just to kind of recap here, okay, we're going to apply Newton's laws to get the acceleration, okay, in order to solve for the displacement, because I want to get to the work. All right, so Bob has an initial velocity of, it says right here, 10 meters per second. He hits this rough patch, which is going to slow him down, and eventually the lawnmower is going to stop. See, so this 10 meters per second, let me start writing out what I know now. Okay, this 10 meters per second is the initial velocity. Okay, the final velocity is equal to 0. Okay, I just solved for the acceleration. I guess I haven't plugged in the numbers yet, but I know what the acceleration is. So from that, I can solve for the displacement. Okay, in order to do that, I'm going back to kinematics. Okay, those are our motion equations. All right, the only thing that I don't know in terms of motion variables is the time, so I'm going to select the timeless equation, which is Vf squared is equal to Vi squared plus 2AD. Notice my final velocity is 0, so my final velocity squared is 0. And so this simplifies a little bit. Vi squared plus 2AD. All right, since acceleration and initial velocity, well, the initial velocity is given, and we did all that Newton work to solve for the acceleration. So all that's left is just that displacement. Okay, so I'll do a little bit of algebra, and that's going to get me the displacement, see? All right. So again, all right, I'd have to go in and sub in my numbers, and I can do that to get the acceleration, and then I would have to go in and sub in some more numbers to get my displacement, but I can do that too. Okay, once I get that displacement, then I can solve for the work. Okay, so as far as the work goes, okay, because that's the question asked, is how much work gets done here. Okay, well, work is going to be equal to force times displacement. Okay, now the one last little kind of sneaky thing, all right, is that the acceleration that we saw for up here, okay, was done by taking our y information from Newton's laws and subbing it into our x information from Newton's laws. So technically speaking here, this is an acceleration along the x direction. These velocities here are along the x direction too, which means the displacement is along the x direction. Bob's pushing the lawnmower sideways. Okay, so lots of little extra subscripts. All right, I'm going to skip them on all the algebra and the intermediate here. Okay, but just as a reminder that, well, when we're talking about work, okay, it's the component of the force that is along the direction or the dimension of the displacement. So I need the x force. Now, what is the x force? Well, that's the sideways pushing from Bob. That x force is the sideways pushing from Bob, which that's Bob pushing times cosine of the angle. Okay, and so to solve for the work, I take that FB cosine of theta and I multiply that by the dx that I solved for above, and that's going to give me my final answer for my work. Okay, so as far as the numbers go, they're all just sitting right here. I don't want to bother going through all the substitution. I'm going to leave that for you, all right? But the initial velocity is given as 10 meters per second. A lawnmower has a mass of 20 kilograms. Here, look at all this stuff. All right, Bob's applying his force 50 newtons down and to the right at an angle of 70 degrees below the horizontal. The coefficient of friction is 30, okay? That would be our kinetic coefficient, by the way. Okay, and then we say, what is the total work done? So now we have everything that we need to solve for these things. Okay, so now it's just an exercise and plugging and chugging. All right, I hope you found that useful. Okay, if you have questions, then just let me know. And this is Mr. Zarzik saying thanks for watching, and I'll see you next time.